This slideshow is about really big earthquakes, earthquakes with a magnitude larger than about 6.5. As you know, these earthquakes produce a lot more shaking than smaller earthquakes, which is why they're so destructive, as shown by the image below. But it turns out that there are other ways in which these earthquakes are also different from smaller ones, and those differences explain why big earthquakes are so difficult to measure accurately. Up to this point, I've been describing earthquake waves as if they're simple sine waves, but in fact they're a lot more complicated than that. They're complicated waveforms like the one shown here in red. Notice that both the amplitude and the apparent wavelength of this wave changes with time. Using a technique called the Fourier transform, it's possible to describe complicated waves like this one as additive mixtures of simple components. For example, we can show that this wave can be created by adding various proportions of 5 simple waves, each of which has a uniform wavelength or frequency. If I add up the blue waves in the right proportions, I get the red wave. This analysis describes the complex pattern of a wave in terms of the abundance of simple waves of a single wavelength or frequency, and is called the frequency spectrum. Frequency analysis is common in music. For example, consider this little clip of music. What's plotted here is the amplitude of vibrations as a function of time. The music is very compressed in this image, so I've shown an enlargement of a tiny period of the sound as well, about 1/3 of a second's worth. If you click on the waveform anywhere, you can hear the music that actually generated it. When you hear the music, you'll hear lots of different notes, and since different notes correspond to different frequencies or wavelengths, you know that these different wavelengths have to be embedded in the waveform, even though it's not very easy to see that. The frequency spectrum makes it easy to see all the different wavelengths or frequencies of sound that make up the clip. Here's what the frequency spectrum of that passage looks like. Now we're plotting the abundance of sound versus the frequency, with low frequencies, the bass, on the left, and high frequencies, the treble, on the right. You can see that the music is mostly composed of low frequencies and that it cuts off at about 15,000 Hertz, which is a frequency of 15,000 cycles per second. Remember that frequency and wavelength are inversely related, so that the high frequencies on the right side of the spectrum correspond to short wavelengths, while the low frequencies on the left side correspond to long wavelengths. Here's the thing. Earthquake waves, even though they have a different origin, can be described in terms of their frequency spectrum exactly like music waves. Just like music, earthquake waves are complex mixtures of low frequency shaking, the earth equivalent of bass, medium frequency shaking, the earth equivalent of mid-range, and high frequency shaking, the earth equivalent of treble. These earthquake waves may include PES or surface waves, but they're all mixtures of waves with different frequencies, just like music. We can use the music analogy to explain the difference between the shaking produced by really big earthquakes and small earthquakes. And when I mean really big, I mean really big. Earthquakes with a magnitude larger than about 6.5, the ones that do most of the damage. It turns out that these really big earthquakes produce shaking that's distinctly different than smaller earthquakes in terms of their frequency spectrum. And it turns out that it's easy to show these differences using the music analogy. So using the music analogy, this is what a small earthquake like the one on the top sounds like. And this is what a big earthquake like the one on the bottom sounds like. Hopefully you noticed that the sound from the big earthquake was different in 3 important ways from the sound produced by the small earthquake. First, it was louder, which means that the amplitude of shaking was greater. This is something you probably already knew. Second, it lasted longer. This is an important point. Big earthquakes last a lot longer than small earthquakes. Small earthquakes often last just a few seconds, while the largest earthquakes can produce shaking that lasts many minutes. And finally, hopefully you notice that the big earthquake produced more low-frequency shaking, or more bass in the music analogy. This is another important difference. Small earthquakes produce primarily high-frequency shaking, while the biggest earthquakes produce lots of their energy in very low-frequency shaking, some of it incredibly low frequency. This difference in the spectrum of shaking explains why the Richter scale isn't very good for measuring the magnitude of really big earthquakes, because it's tuned to the high-frequency vibrations only. All of the energy in the low-frequency components of shaking are completely lost to the Richter scale, so it underestimates the strength of the earthquake. Remember, too, that the Richter magnitude depends only on the amplitude of shaking, not its duration, so that the additional energy required to create a longer period of shaking is also lost on the Richter magnitude scale. For these reasons, seismologists don't use the Richter scale anymore, and certainly not for very large earthquakes for which the Richter scale will always underestimate their magnitude.